Hello everyone, welcome to Biochemia web channel. I'm here with the topic titled Redox and Organic Reactions, Thermodynamics and Kinetics. And please don't forget to like the video to reach more people. I wish it to be useful. Let's start. In this topic, many contents welcome us, and we have got four major titles. The one is Redox Reactions, then Organic Reactions, the second major title, which we have subtitles, the type of organic reactions, bond breaking and bond making, bond cleavage, radicals, carbocations and carbanions, and bond formation. The third title is Thermodynamics, which we will talk about energy and units of energy, thermodynamic systems, internal energy and enthalpy, bond dissociation energy, and at the end, enthalpy and entropy. The fourth and the last major title is Kinetics of Chemical Reactions, Energy of Activation, Rate Equations, Catalysts, Factors Affecting Reaction Rate, and Enzymes. So these are the topics. Let's start with the first title, Redox Reactions, Reduction and Oxidation Reactions. A common type of chemical reaction involves the transfer of electrons from one element to another. These reactions involve oxidation and reduction. Oxidation is the loss of electrons from an atom. Reduction is the gain of electrons by an atom. Oxidation and reduction are opposite processes, and both occur together in a single reaction called an oxidation reaction and reduction reaction, or shortly, redox reaction. This is a critical knowledge. Both occur together in a single reaction. So we cannot separate them, or we cannot say they are separate reactions. A redox reaction always has two components, one that is oxidized and one that is reduced. A redox reaction involves the transfer of electrons from one element to another. And here's an example. Zinc reacts with copper, and here zinc loses two electrons. It loses two electrons to form the ionized form. So this means zinc is oxidized. And the copper gains two electrons, to form, this is the ionized metal, ionized copper to form the copper metal. So the copper is reduced. Each of these processes can be written as individual reactions called half reactions to emphasize which electrons are gained and lost. And here you see the oxidation half reaction with zinc, loss of which here you see the loss of two electrons from zinc. Thus, this means zinc is oxidized. And here, as you see, the reduction of half reaction of copper, which gain electrons. So the copper is reduced. A compound that gains electrons, which means is reduced, while causing another compound to be oxidized, is called an oxidizing agent. So this means here the copper is reduced, and thus the copper is an oxidizing agent. It causes oxidation of zinc. A compound that loses electrons, which means oxidized, as you see, the zinc is oxidized, while causing another compound to be reduced, is called a reducing agent. This means zinc is a reducing agent because it cause the reduction of copper. When considering natural atoms, metals lose electrons and nonmetals gain electrons. When considering ions, cations tend to gain electrons and anions tend to lose electrons. In the past, redox events were called combustion, and if this event occurred in metals, as seen here, it was called rusting. Similarly, in the human and animal organism, redox phenomena have been described as the slow burning of foodstuffs or shortly burning of foodstuffs. Many common processes involve oxidation and reduction, or shortly redox reactions. For example, common antiseptics such as iodine and hydrogen peroxide are oxidizing agents that oxidize to clean wounds and thus kill bacteria that can cause effect. And here in the picture, which there you see the illustration of rust formation. So when iron rusts, it occurs. This means it is oxidized by oxygen in the air to form iron oxide, oxidized with water. So this is in the ferric state. And in this redox reaction, natural atoms are oxidized to ferric cations and elemental oxygen is reduced to oxygen ions. And rust is the general name given to compounds of iron and oxygen formed in the presence of water and air. Different forms of rust can be detected visually or by spectroscopy and can form under different conditions. And rust contains hydrated iron oxide, water, and iron oxide, hydroxide. Rust is a collective term for the corrosion of iron and its alloys such as steel. In some reactions, it is much less apparent which reactant is oxidized and which is reduced. For example, here, in the combustion of methane, the component of natural gas, with oxygen, or methane react with oxygen to form carbon dioxides and water molecules. And as you see here, there are no metals or cations that obviously lose or gain electrons. Yet, this is a redox reaction. In these instances, it is often best to count the oxygen and hydrogen atom. So, oxidation results in correction. Oxidation reaction results in the gain of oxygen atom or the loss of hydrogen atom. And here, as you see in the reaction steps, the methane lose electrons, lose hydrogen, and gain oxygen, which the methane is oxidized. So this reaction results in an increase in the number of C, which is carbon, and the Z, which refers an electronegative atom such as oxygen, and it's usually oxygen, or a decrease in the number of carbon hydrogen bonds, increase in the number of carbon oxygen bonds, and increase and decrease in the carbon hydrogen bonds as seen here. So losing hydrogen, gaining oxygen. Reduction, focus on the oxygen, results in the loss of oxygen atoms or the gain of hydrogen atoms. So in reduction, loss of oxygen atoms or the gain of hydrogen atoms. And here the oxygen gain four hydrogen atoms. Thus, oxygen is reduced in this reaction. And this kind of reaction results in a decrease in the number of C carbon Z double bonds, that's not double bonds, sorry, single bonds, so usually carbon oxygen, or increase in the number of carbon hydrogen bonds. And here is a reduction and oxidation reactions occur in two different directions from left to right. Focus on from left to right. As you see, after each reaction step, number of carbon oxygen bond increases and number of carbon hydrogen bond decreases. And so this is the oxidation, increasing number of carbon oxygen bonds. So here this is the methane, and can be oxidized by replacing carbon hydrogen bonds with the carbon oxygen bonds, as seen here, carbon oxygen bonds. And this will produce an alcohol, the methanol. And if oxidation continues, it will provide its aldehyde, this formaldehyde or the methanol. And if continues, this is the carboxylic acid, methanoic acid, or the formic acid. And at the last step, carbon dioxide is produced. And if we follow the reaction steps from right to left, these are the reduction. As you see, the number of carbon hydrogen bonds increases, or the increasing number of carbon hydrogen bonds. And reduction of an alkene forms an alkane by addition of hydrogen. This is called hydrogenation. It's a type of reduction. I mean, we will discuss in the alkanes and alkenes. If there's an alkene, which means there's a carbon-carbon double bond, if we put hydrogen, it's a kind of reduction. So it will produce a alkane. This is called hydrogenation. Another example for reduction, or if it's oxidize and alkene to alkene. Biological importance of redox reactions. The continuity of life is achieved by converting the chemical energy gained from food into other forms of energy. And remember the general equation that we use glucose to produce ATP. And this is occur via redox reactions. There are too many redox reactions occurs in the pathway of glucose conversion to ATP and carbon dioxide and water, especially we need oxygen for that kind of reaction. These transformations are achieved by oxidation of foodstuffs. And transformation occurs in mitochondria, the power plant of the cells. The most important oxidation agent is oxygen, and during the combustion of fossil fuels such as coal or oil, sulfur dioxide is formed from the sulfurous compounds. And sulfur dioxide forms sulfurous acid when exposed to moisture in the air, and sulfurous acid is also oxidized to sulfuric acid. And the sulfuric acid reacts with the carbonaceous materials of the buildings, causing them to disintegrate. And sulfuric acid, which reaches the soil with rainwater, forms water-soluble sulfuric compounds with heavy metal ions. And these compounds are harmful to the roots of many plants and cause forest death. So in every aspect of life and also for the earth, redox reactions are uh, very significant. So we finished the first major title. Organic reactions, the second title of the topic. Reactions are at the heart of organic chemistry. An understanding of chemical processes has made possible the conversion of natural substances into new compounds with different and sometimes superior properties. Aspirin, ibuprofen, nylon, and polyethylene are all products of chemical reactions between substances derived from petroleum. Chemical reactions are equilibrium reactions. Products with different physical and chemical properties are formed from a starting material, an initial product. Like other reactions, equations for organic reactions are usually drawn with a single reaction arrow between the starting material and product. But other conventions make these equations look different from those encountered in general chemistry. The region, the chemical substance with which an organic compound reacts, is sometimes drawn on the left side of the equation with the other reactants. And chemical reactions preferably occur in liquid media. I know this is universal for the life, for the continuity of life. We need water, and water provides the aqueous or liquid media for the occurrence of chemical reactions. There are some criteria to be considered when writing an equilibrium reaction. Regions and products are written. The reaction is equalized. The phases of the substance are indicated. The temperature at which the reaction occurs is indicated. The heat of reaction should be given, and parameters such as pH, ion strength, or ionic strength of the solution are indicated, and other reactions that may occur are considered. Organic molecules undergo substitution, elimination, and addition reactions. And like other compounds, organic molecules also undergo acid-base reactions that we discussed in the previous topic, ion oxidation reduction reactions we discussed in the previous slides. And also there are other types, the arrangement, condensation, polymerization, pericyclic reactions, etc. But all are related to substitution, elimination, addition type of reactions. And the first one is the substitution reaction. Substitution is a reaction in which an atom or a group of atoms is replaced by another atom or group of atoms. We can also say it's a replacement reaction. And in a general substitution reaction, the Y replaces Z on a carbon atom. And Z equals hydrogen or a heteroatom. And in general, Z is an electronegative atom. And here are some examples for the replacement or substitution reaction. And substitution reaction involves sigma bonds, which are mean that we will discuss in the following topics. The double bond of the single bond formed with the carbon is called the sigma bond. It's called the sigma bond. If the carbons forms double bond, the first one is the sigma bond. This is the second one, which forms a double bond, is the p bond, or pi bond. And in the replacement reactions, I said involve sigma bonds. So one sigma bond breaks and another forms at the same carbon atom as seen here. This will be broken and the new one is occurred. And the most common examples of substitutions occur when Z is hydrogen or a heteroatom that is more electronegative than carbon, more electronegative than carbon. And here you see the iodine replaced with the chloride. Thus, a halogen or a haloalkane is converted to another haloalkane. So iodomethane reacts with the chloride to form the chloromethane and iodide. And in this reaction step, as you see, this is the acetyl chloride reacts with the hydroxide, and at the end, the acetic acid and chloride ion occurs. So the hydroxide replaces chloride. Elimination reactions. Elimination is a reaction in which elements of the starting material are lost and the p bond is formed. In an elimination reaction, two groups X and Y are removed from a starting material. And here is the general elimination reaction. An organic compound undergo reaction with reagent, and X and Y is removed, are eliminated from the organic compound. So this means two sigma bonds are broken. And the products are a p bond formed with at the point of X and Y removed, and X and Y form a new compound as a product. Two sigma bonds are broken and the p bond is formed between hydrogen atoms. The most common examples of elimination occur when X is hydrogen and Y is a heteroatom more electronegative than carbon. And here is a common example, and this is an ethanol, an alcohol, reacts with the sulfuric acid to form the ethylene and the water molecule. So the hydrogen and the hydroxide here, X and Y, this is X, this is Y, broken, that's two sigma bonds broken. And the P bond is occurred between the two carbon atoms here and the water molecule. And so an ethanol, which is a alcohol which belongs to the functional group family, which carrying a heteroatom single bond to the carbon, is converted to a hydrocarbon. It's ethylene. It's an alkene. This means, in general, and this means elimination reactions give alkenes. Another example here: loss of hydrogen bromide. The other also hydrogen and bromide, X and Y, and a p bond occurred. So a haloalkane will yield an alkene. A cycloalkane ring structure, but it's not alkane because there is an alcohol, so cyclic alcohol. Removing the X and Y, which will be water and the P bond, the cycloalkene. Addition reaction. Addition is a reaction in which elements are added to a starting material. In an addition reaction, new groups X and Y are added to a starting material. And this is the general addition reactions. And I think you can consider that this is the opposite or the inverse of elimination reaction. And here, in addition, a p bond is broken to put the X and Y with two sigma bonds. And here are the examples. The p bond is broken and hydrogen bromide react with the ethene to give the haloalkane. And here, this is another p bond broken and water molecule is added to produce an alcohol. So it's easily understandable that the addition and elimination reactions are opposite type of reactions. Yes, addition and elimination reactions are exactly opposite. A p bond is formed in elimination reactions, whereas the p bond is broken in addition reactions. And here you see the diagram. Elimination form a p bond in this way, and the addition is the opposite, breaking the p bond to form two sigma bonds. Bond breaking and bond making. A reaction mechanism is a detailed description of how bonds are broken and formed as a starting material is converted to a product. A reaction mechanism describes the relative order and rate of bond cleavage and formation. It explains all the known facts about a reaction and accounts for all products formed, and it is subject to modification or refinement as new details are discovered. A reaction can occur either one step or in a series of steps. A one-step reaction is called a concerted reaction. No matter how many bonds are broken or formed, a starting material is converted directly to a product. And an example is, consider we have a starting material A directly converted to product B. This is a concerted reaction, one-step reaction. A stepwise reaction involves more than one step. A starting material is first converted to an unstable intermediate called a reactive intermediate, which then goes on to form the product. This means we have a starting material A. We first convert it to, for example, the alpha in intermediate, and then alpha converted to the B. So this is a reactive intermediate. And there may be more than one reactive intermediate, such as, for example, A to alpha, then beta, then delta, and bravo. And this happens in organisms. There are reaction steps, there are concerted reactions, and also stepwise reactions. Bond cleavage. Bonds are broken and form in all chemical reactions, no matter how many steps there are in the reaction. However, there are only two ways to break a bond. The electrons in the bond can be divided equally, the first way, or unequally, the second way, between the two atoms of the bond. And the consequences of dividing equally or unequally bonds are different. Breaking a bond by equally dividing the electrons between the two atoms in the bond is called homolysis or homolytic cleavage. And here you see we have a AB molecule which undergoes homolytic cleavage, and each electron is equally shared by each atom, or each atom gets one electron. Breaking the bond by unequally dividing the electrons between the two atoms in the bond is called heterolysis or heterolytic cleavage. And here, heterolysis of a bond between A and B, now we have a heterolytic cleavage, can give either A or B the two electrons in the bond. So this means in this example, B gets two electrons. A gets two electrons in this example. And when A and B have different electronegativities, the electrons normally end up on the more electronegative atom. So here, as you see, A and B do not share electrons equally. Only the one gets both electrons, B or A. Homolysis and heterolysis require energy. Both processes generate reactive intermediates, but the products are different in each case. And consider the type of cleavage. In homolysis, there's only one possibility, but in heterolysis, there are two possibilities. This means there are three different products in total. And one product of homolysis, but heterolysis, there are two products or two possible products. Homolysis generates uncharged reactive intermediates with unpaired electrons. Heterolysis generates charged intermediates. Each of these reactive intermediates has a very short lifetime. This means each reacts quickly to form a stable organic compound or organic product. So they are unstable and have a very short lifetime. And here you see how we can illustrate the movement of the electrons. So in homolizers, which the electrons are shared, one by A and one by B here, we use two, as you see here, two half-headed, look at the head of the arrow, half-headed curved arrows to represent the two single electrons shared equally by A and B. In the heterolizers, which B or A gets both electrons, look at the head, one full-headed curved arrow is needed for one electron pair. And here the B gets the electrons and has a negative charge, and A get a positive charge. This is why in heterolizers, the products are charged. But in homolizers, they carry unpaired electrons. And to illustrate the movement of a single electron, which we use here the in homolizers, half-headed curved arrow, sometimes it is called phi shoe. Phi shoe. Radicals, carbocations, and carbanions. These are the products of homolizers and heterolizers. But which one? Homolizers of the carbon Z bond generates two uncharged products with unpaired electrons, and a reactive intermediate with a single unpaired electron is called a radical. So the product of homolizers is a radical. Most radicals are highly unstable because they contain an atom that does not have an octet of electrons. Remember the octet rule from the general chemistry topic. Radicals typically have no charge. They are intermediates in a group of reactions called radical reactions. Heterolizers of the carbon Z bond can generate a carbocation or a carbanion. So the cation, the positive charge, carbon, and carbanion negative charge, carbon. Giving two electrons to Z and none to carbon generates a positively charged carbon intermediate. It is called carbocation. Giving two electrons to carbon, so now the carbon gets the electrons, and none to Z, generates a negatively charged carbon species called a carbanion. Both carbocations and carbanions are unstable reactive intermediates. A carbocation contains a carbon atom surrounded by only 6 electrons. A carbanion has a negative charge on carbon, which is not a very electronegative atom. And carbocations and carbanions, electrophiles and nucleophiles, remember the Lewis acid, we did the definitions, can be intermediates in polar reactions. Reactions in which a nucleophile reacts with an electrophile. This means transfer of electrons. And here you see all products, and here the first is the homolizers. Half-headed railroads. So we have a radical, a carbon and Z radical. And in heterolizers, which is the transfer of electrons shown here after bond cleavage with the full-headed curved arrow. So here the Z gets both electrons, which the carbon here forms the carbocation. If the carbon gets the electrons, it will be carbon. So free reactive intermediates resulting from homolizers and heterolizers of carbon Z bond is shown in this illustration or in this figure. Homolizers and heterolizers generate radicals, carbocations, and carbanions, the three most common reactive intermediates in organic chemistry. Radicals and carbocations are electrophiles because they contain an electron-deficient carbon. And carbonions are nucleophiles because they contain a carbon with a lone pair. And here the radical carbocation, which they have no octet rule or has no octet, but in carbonion has an octet with lone pair. Bond formation. Like bond cleavage, bond formations occur in two different ways. Two radicals can each donate one electron to form a two-electron bond. Alternatively, two ions with unlike charge can come together with the negatively charged ion donating both electrons to form the resulting two-electron bond. And bond formation always releases energy. And here you see forming a bond from two radicals, one electron comes from each atom. And forming a bond from two ions, both electrons come from one atom. And with this slide, we've finished the organic reactions title. It's time for thermodynamics, and these are the subtitles: energy and units of energy, systems, internal energy, and etc. And also, there's a term that I want to express: thermochemistry, which is the study of energy in chemical reactions. And thermochemistry is a subdiscipline of thermodynamics. For a reaction to be practical, the equilibrium must favor the products, and the reaction rate must be fast enough to form them in a reasonable time. These two conditions depend on the thermodynamics and the kinetics of reaction respectively. That we will have titles for both of them. Here we are in the thermodynamics. Thermodynamics describes energy and equilibrium. And thermo derived from thermal, heat, or related to temperature. And dynamics means behavior, properties of temperature, and how it behaves. So, in general, it is the science of heat and temperature that deals with energy and work. It studies how different forms of energy are converted into each other. Or in other words, thermodynamics is the science that studies the relationship between heat and work. So thermo means heat, which represents the energy, heat of energy, and dynamics represent work. And kinetic describes reaction rates. Energy is the capacity to do work. And there are two types here given: potential energy, which is stored energy, and kinetic energy is the energy of motion. And total energy in a system does not change. Energy cannot be created or destroyed. And this is the first law of thermodynamics. So there are laws of thermodynamics, and this is the first law. And here in this illustration, potential energy and kinetic energy, or conversion of potential energy to kinetic energy, or their relationship, is explained. When a ball is thrown into the air, it possesses kinetic energy, which is converted to potential energy as it reaches the maximum height. As you see here, the kinetic energy is transferred from the thrower's hand to the baseball. And the kinetic energy is converted to potential energy as the ball rises. All of the ball's kinetic energy is converted to potential energy when it reaches the maximum height. And when the ball descends, the potential energy is converted back to kinetic energy. So here, when the ball starts to descend, potential energy starts to be converted to kinetic energy. And when the ball hit to the ground, some of the kinetic energy is transferred to the ground. Maybe it's transferred to the sound energy, etc. And this kinetic energy or potential energy continue, the conversion relation continue until the ball rests motionless on the ground. When the motionless state occurs, this means all kinetic energy is transferred to the potential energy. During a chemical reaction, energy can be used, produced, transported, such as heating and cooling, or energy forms can be interconverted. And heat is the energy that passes from the boundaries of a system at a certain temperature to a system at a lower temperature, from high to low, due to temperature difference. So heat, like work, is a form of energy transfer. And the temperature is a measure of the hotness or coldness of an object. It's a measure of the average molecular kinetic energy of a system. And for gases, the kinetic energy is proportional to their absolute temperature. And here are some examples of the energy conversion, such as heat energy to mechanical energy in trains, for example, chemical energy to heat energy, combustion, chemical energy to mechanical energy, light energy to chemical energy, photosynthesis, and electrical energy, chemical energy accumulator. Another example, think about or imagine a weightlifter. A weightlifter transfers the chemical energy from ATP into kinetic energy. It moves the muscle and lifts the barbell. While holding it steady, the kinetic energy is converted to potential energy, and it even generates heat. So it generates heat and work. Energy and units of energy. Joules and calories are used as units of measurement for energy form. And 1 calorie is equal to the amount of energy required to increase the temperature of 1 gram of water by 1 degree Celsius. And the conversion of 1 calorie to joule is 1 calorie means it's 4.184 joules. The energy contained in food is measured in nutritional calories. It's in capital letter S, nutritional calories. And one nutritional calorie equals 1000 thermodynamic calorie or 1 kilocalorie. And dietary calorie or the nutritional calorie is a unit of energy commonly used to describe the energy content of food. And the thermodynamic or physical unit calorie is the energy to require the temperature of what I said 1 gram of water by 1 degree Celsius. And so this definition is derived as temperature of 1 kilogram of water by 1 degree Celsius for the nutritional calories. It is common practice to use only the unit kilocalorie to avoid confusion between the physical calorie and the nutritional calories. And here's some example about the macromolecules or the fuel molecules we need, the amount of energy that they can give us. And 1 gram of carbohydrates or proteins provides 4 kilocalorie per gram energy, and lipids provide 9 kilocalorie per gram energy. Thermodynamic systems. Changes of energy forms are studied in thermodynamic systems. A thermodynamic system is defined as a quantity of matter or a region in space that is of interest. And system, as you've seen here in the illustration, is a region containing energy and or matter, energy and matter, that is separated from its surroundings by arbitrarily imposed Volov's boundary. So there's a boundary which forms, which separate the system with the surroundings. The mass or region outside the system is called surrounding. Everything that interacts with the system, in other words, surrounding is everything that interacts with the system. And the surface that separates the system and the surrounding is called the boundary. A boundary is a closed surface surrounding a system from which energy and mass may enter or leave the system. So the universe means the universe, right? So the universe calls the system plus surrounding. And systems are classified as isolated, closed, and open systems. Isolated systems are not permeable to energy and matter, such as thermos. Closed systems are permeable for energy, impermeable for matter, such as light bulb. Only energy is changed. And open systems permeable for energy and matter. So we are the examples for an open system. And a good explanation, a good illustration to explain the isolated, closed, and the open system. And the red arrows indicate exchange of energy, and the blue arrows indicate exchange of matter. And in an isolated system here, reactants, folks, think about the reactants which are present in a thermos flask or an insulated vessel, where neither energy nor matter is exchanged with the environment. Another example, if the piston and the cylinder arrangement in which the fluid like air or gas is being compressed or expanded is insulated, it becomes an isolated system. And so there is no exchange of energy and matter. In a closed system, reactants placed in a closed vessel made of materials like steel, copper, and silver are an ideal example of a closed system, since the material of the vessel is conducting in nature. A cylinder in which the valve is closed is an example of a closed system. When the cylinder is heated or cooled, it does not lose its mass, but exchange of energy occurs, not the exchange of matter. And in an open system, consider a beaker in the presence of reactants and consider an open beaker. Here the boundary is an imaginary surface enclosing the beaker and the reactants. So it will be an open system. It's an open system. An exchange of energy and matter happens. Another example, a steam turbine, a pool with water, where the water can enter or leave the pool. And the best example for the open system is animals, humans, plants. Internal energy and enthalpy. And first law of thermodynamics. Energy cannot be created from nothing and destroyed from nothing. It can only be transformed. And the thermodynamical studies also the differences between the initial and the final state of a system. And it's about the energy. The sum of the heat and work given or taken from the system to the environment is equal to the changes in the internal energy of the system. And in an isolated system, here the U represents internal energy, of the system. And the delta means change. So in an isolated system, energy change in a given time is equal to zero, or internal energy is constant and there is no change in internal energy. It means that the heat and work done are the same. So the internal energy has not changed. Every system has a certain energy called internal energy, which is a property of the system. There can be change in internal energy, such as a transfer of energy from one system to another. And internal energy can be transferred either as heat, which is represented as Q, or work, A or W. There were two formulas calculating or presenting the change in internal energy and heat and work, which don't forget, this is internal energy, this represents the change, delta, Q is the abbreviation for heat, and W is work. Mostly work is done when a chemical reaction occurs. Also, this is the principle of the enzymes, this is the principle of life. Since work and heat are both energy, we must consider both of them. And there are two possibilities here, two different formulas, but at the end they will have the same meaning. So the internal energy change is equal to the heat minus work. In this case, work is done and energy is lost or transferred. And for the equation, internal energy change is equal to heat plus work. In closed systems, an energy change occurs, and the value found is plus if energy is taken into the system from outside, negative energy is given from the system to the environment. The internal energy of a system can be increased by heating and decreased by cooling. And in terms of work, electrical work and volume changes are generally encountered. And in fact, when we consider the both formulas, both will lead to the same result. If work is done on the system, it gains energy. When heat is given to the system, it loses energy. You need to get heat of energy, heat to gain energy. If we use the plus in an equation, work is done on it. That is, energy is transferred, so endothermic. If the negative, it releases exothermic. So this means if I do work, energy is lost. So W or work is positive if work is done on the system. W is negative if work is done by the system. So in negative, work is done by the system. In positive, work is done on the system. Enthalpy is the measurement of energy in a thermodynamic system. Now we will express the measurement of energy in enthalpy, H. The amount of enthalpy is equal to the total heat content of a system and is equivalent to the internal energy of the system plus the product of volume and pressure. It's equivalent to the internal energy of the system plus the product of volume and pressure. Technically, enthalpy describes the internal energy required to create a system and the amount of energy required to make room for it by creating its pressure and volume and changing its environment. And so by modifying the equation given in the previous slides, the internal energy change is equal to enthalpy change, plus volumetric work. And we can express work by the product of volume and pressure. And if we omit the changes, enthalpy equals to internal energy plus pressure and volume. When a process starts at constant pressure, the heat released, actually heat may absorb or release, is equal to the enthalpy change. The enthalpy change is the sum of the product of internal energy denoted by U and the volume and pressure, product of volume and pressure denoted by P and V, and is expressed as follows. So enthalpy change is equal to change in internal energy plus change in product of pressure and volume. Enthalpy is also defined as a state function based entirely on the state of the function, internal energy, pressure, volume. It is normally represented by the enthalpy change delta H between the initial and final states of the process. And look at this formula. The delta sign, the place of delta sign is change. If pressure do not change throughout the process, and the task is limited by the pressure and the volume, the enthalpy change is given by the enthalpy change equals the change in internal energy times sum plus pressure times volumetric change. Another representation, an energy change or enthalpy change equals to Q. Q represents, the small letter Q represents the heat flow. The heat flow at constant pressure in a process is equal to the enthalpy change. And this is the formula. And the relationship between the small letter Q, which is the heat flow, and the enthalpy change can be defined by knowing whether the heat flow is endothermic or exothermic. An endothermic reaction is one that absorbs heat and reveals that heat is consumed from the environment in the reaction, and hence Q will be greater than 0 or positive. If Q is positive, then the enthalpy change is also positive for the equation at constant pressure and temperature. Similarly, if heat is released as an exothermic reaction, heat is given to the environment. So therefore, Q will be slower than 0 and negative. So if Q is negative, energy change and enthalpy change will be negative. Bond dissociation energy. Bond breaking can be quantified using the bond dissociation energy. And the bond dissociation energy is the energy needed to homolytically cleave a covalent bond. The energy absorbed or released in reaction symbolizes the enthalpy change or heat of reaction. So enthalpy can be explained by the formation of bonds or bond dissociation energy. When the enthalpy change is positive, energy is absorbed and the reaction is endothermic. When the enthalpy change is negative, energy is released and the reaction is exothermic. Bond dissociation energies are always positive numbers and homolysis is always endothermic. Conversely, bond formation always releases energy, so the reaction is always exothermic. Comparing bond dissociation energies is equivalent to comparing bond strength. The stronger the bond, the higher its bond dissociation energy. And here is an example. in the way the bond breaking, which is endothermic, and we have an enthalpy change positive number, thus energy is needed. And the inverse way, which look at the radicals to form the energy, to form the bond or bond making, the enthalpy change is in negative values, thus energy is released, and bond making is exothermic. Bond dissociation energies decrease down a column of the periodic table as the valence electrons used in the bonding are farther from the nucleus. In some example, the haloalkanes, the fluoromethane, chloromethane, bromomethane, iodomethane, and increasing the size of the halogen, as you see, decrease the enthalpy change. And from iodine to fluorine, from right to left, as you see, the enthalpy change, energy increasing, so increasing the bond strength. So increasing the size of the halogen decreases bond strength. Because the bond length increases down a column of the periodic table. And the bond dissociation energies are a quantitative measure of the general phenomenon. So shorter bonds are stronger bonds. Bond dissociation energies are also used to calculate the enthalpy change in a reaction in which several bonds are broken and formed. So to calculate the overall enthalpy change. Enthalpy change indicates the relative strength of bonds broken and formed in a reaction. And when positive, more energy is needed to break bonds than is released in forming bonds. The bonds broken in the starting material are stronger than the bonds formed in the product. When the enthalpy change is negative, more energy is released in forming bonds than is needed to break bonds. The bonds formed in the product are stronger than the bonds broken in the starting material. Well, the overall enthalpy change of a reaction is equal to sum of the enthalpy change of bonds broken plus sum of the enthalpy change of bonds formed. And here's an example. As you see, the third butyl chloride reacts with water, and the products are third butyl alcohol or 2-methyl-2-propanol plus hydrochloric acid. And here the enthalpy change in the side of bonds broken, the starting materials, enthalpy change of terbutyl chloride and water molecule, and the total is plus, as you see, 829 kilojoule per mole. And at the product side, so this is plus, so energy needed to break the bonds. And at the product side, which the bonds are formed, and for each, you see the enthalpy change at minus decrease, so energy released in forming bonds. And at the end, the overall enthalpy change, so the sum in the side of bonds broken and plus sum in the side of bonds formed, the answer will be minus 3 kilojoule per mole. So this is the enthalpy change of overall reaction. And as you see, it's a negative value. So this means in total, the reaction is exothermic and energy is released. The bonds broken in the starting material are weaker than the bonds formed in the product. Equilibrium constant and free energy changes. The equilibrium constant, which is represented as KUK, E and Q, equilibrium constant, K means constant, is a mathematical expression that relates the amount of starting material and product at equilibrium. It is another way to evaluate or to assess the equations, the chemical equations or chemical reactions. When starting materials A and B react to form products C and D, the equilibrium constant is given by the following expression. So A plus B, C plus D. So this is the part of starting material and the product. So the equilibrium constant is equal to the concentration of the products divided by the concentration of reactants. That's the concentration of C times concentration of D divided the product of concentration of A and B. This will give the equilibrium constant. And the size of the equilibrium constant tells about the position of equilibrium. That is, it expresses whether the starting materials or products predominate once equilibrium has been reached. When the equilibrium constant is greater than 1, equilibrium favors the products C and D, and the equilibrium lies to the right as the equation is written. When equilibrium constant is smaller than 1, equilibrium favors the starting materials A and B, and the equilibrium lies to the left as the equation is written. And for the reaction to be useful, the equilibrium must favor the product, thus must be over 1. The position of equilibrium is determined by the relative energies of the reactants and products, and the free energy of a molecule, also called its Gibbs free energy, which is symbolized by G. And the Gibbs free energy means also the free enthalpy or free energy. And it is established by Josiah Willard Gibbs, an American scientist, and he contributed significantly into disciplines of physics, chemistry, and mathematics. The change in free energy between reactants and products, symbolized by delta G, determines whether the starting materials or products are favored at equilibrium. So the Gibbs free energy, or change in Gibbs free energy, or change in free enthalpy, is the overall energy difference between reactants and products. So this means the energy change, free energy change, is equal to free energy of the products minus free energy of the reactants. And free energy change is related to the equilibrium constant by the following equation. And free energy change is equal to minus 2.303 times R, represents the gas constant, times temperature, Kelvin temperature, and times the log equilibrium constant. And every reaction is a constant at a given temperature. And the G varies with the concentration of reactants and the reactant. When the equilibrium constant is over 1, which makes the log equilibrium constant is positive, making free energy change negative, and energy is released. Thus, equilibrium favors the products. When the equilibrium constant below 1, which makes the log equilibrium constant is negative and making energy change, free energy change positive, and energy is absorbed, thus the equilibrium favors the reactants. Compounds that are lower in energy have increased stability. Thus, equilibrium favors the products when they are more stable, lower in energy, than the starting materials of a reaction. Another title, Enthalpy and Entropy. In order for a physical and chemical event to start, the initiation force of motion in isobar and isothermic phenomena is the free enthalpy that we described. And free enthalpy is determined by enthalpy and the second factor, entropy, which is a measure of stability or measure of instability. So the free energy change depends on the enthalpy change and the entropy change. And entropy is indicated with S. So enthalpy change indicates relative bond strength. But what does entropy change measure? Entropy is a measure of the randomness in a system. The more freedom of motion or the more disorder present, the higher the entropy. And here the second law of thermodynamics welcome you. The entropy of the universe always increases. And the entropy change is the measure of instability that exists in a system. And the entropy of the universe, according to the second law of thermodynamics, is always increasing. Increasing instability in the system leads to an increase in entropy. Think about the gas molecules move more freely than liquid molecules, and their entropy is higher. Cyclic molecules have more restricted bond rotation and lower entropy than similar acyclic molecules. And the Gibbs free energy or the free energy change, which depends on the enthalpy and entropy. And the entropy, another definition or an alternate definition, is the disorder of a system, which is related to the number of states in which the system can exist. And the entropy change is a macro state variable, and its unit of measurement is joule per Kelvin. So more states means more energy. And the entropy of the universe is always increasing, as I said. So this means the universe we have universe with more states. The entropy change is the change in the amount of disorder between reactants and products. And if it is positive, the products are more disordered than the reactants. And entropy is negative. Entropy change is negative when the products are less disordered than the reactants. And the reaction resulting in an increase in entropy are favored. And this is important for the continuity of the life. And here is the equation. Relates enthalpy change, entropy change, and Gibbs free Gibbs energy change and temperature. And here don't forget temperature is the Kelvin temperature. So the total free energy change is equal to enthalpy change minus temperature times entropy change. And this equation tells us that the total energy in a reaction is due to two factors. The change in the enthalpy change, this means the bonding energy, and the change in disorder. When a single starting material forms two products, as in the homolytic cleavage of a bond to form two radicals, entropy increases and favors formation of the products. In contrast, entropy decreases when an acyclic compound forms a ring, because the ring has fewer degrees of freedom. In this case, therefore, entropy does not favor formation of the product. In the illustration, the entropy increases and favors the products. In here, a single reactant forming two radicals. But if the X and Y react to form a ring structure, a cyclic structure, which means a more restricted motion, so entropy decreases and favors the reactants, And by this slide, we finish the thermodynamics. Kinetics of chemical reaction, the fourth and the last major title of the topic. Kinetics of chemical reactions, or shortly kinetics. The study of reaction rates is called kinetics. Kinetics cover the rate of reaction, time-dependent occurrence of a reaction, and the reaction pathway, the mechanism. And reaction rate, shortly RR, the change in concentration per unit time. It is defined as the change in concentration per unit time. Energy of activation. It is the energy difference between the reactants and the transition state. It is the energy barrier that must be exceeded for reactants to be converted to products. It is also called activation enthalpy. Activation energy applies to reactions in constant volumes. The lower the activation energy value, the faster the reaction proceeds. If several reaction pathways are possible for a reaction, the reaction takes place via the pathway with the lowest activation enthalpy. And the larger the energy of activation, the slower the reaction. Concentration and temperature also affect reaction rate. The higher the concentration, the faster the rate. Increasing concentration increases the number of collisions between reacting molecules, which in turn increases the rate. The higher the temperature, the faster the rate. Increasing temperature increases the average kinetic energy of the reacting molecules, because the kinetic energy of colliding molecules is used for bond cleavage. Increasing the average kinetic energy increases the rate. The rate of a chemical reaction is determined by measuring the decrease in the concentration of the reactants over time, or the increase in the concentration of the products over time. A rate law or rate equation is an equation that shows the relationship between the rate of a reaction and the concentration of the reactants. A rate constant, K constant, is a fundamental characteristic of a reaction. It's a complex mathematical term that takes into account the dependence of a reaction rate on temperature and the energy of activation. Fast reactions have larger rate constants. Slow reactions have small rate constants. Catalyst. Some reactions do not occur in a reasonable time unless a catalyst is added. A catalyst is a substance that speeds up the rate of reaction. A catalyst is recovered unchanged in a reaction. This is so important. Unchanged in a reaction. And it does not appear in the product. So here I want to put a star. This is important. The catalyst is recovered unchanged in a reaction and it does not appear in the product. In the presence of catalyst, a new reaction pathway with a lower activation energy is open. In this way, the reaction rate is increased. The reason for the increase in the rate is that the energies of more particles exceed the energy of activation value. And common catalysts in organic reactions are acids and metals. Catalysts act selectively and cannot equally accelerate all reactions that can proceed normally. This effect is particularly pronounced with biological catalysts, which not only accelerate the reaction but also direct it. And enzymes catalyze certain specific reactions. The most important properties of enzymes are their catalytic power and specificity. So enzymes are the biological catalysts for living creatures. Factors affecting reaction rate and temperature is the concentration. Chemical reactions are affected by temperature, and one increase about 10 degrees leads to doubling of the reaction rate. This is primarily due to an increase in the number of particles with sufficient activity and to a lesser extent to an increase in the probability of particles colliding with each other. At higher temperatures, the number of particles with energies higher than energy of activation increases and more particles react per unit time. And here was a graph showing the reaction coordinate, and as you see, there will be no change in the reaction coordinate under the action of catalyst, under the action of enzyme. So there are reactants and products. The change is about the energy required for the activation, which is called activation energy. And in an uncatalyzed reaction, look at it need more energy. For the catalyzed reaction, the energy of activation decreased. So the lower EA, faster reaction, larger EA in uncatalyzed reaction, slower reaction. The reaction rate is also related to the surface width of the reactant. The smaller the diameter of the particles, the higher the RR, the operational reaction rate. This increase in the reaction rate is due to the increase in the number of particles encountered per unit time, and this phenomenon is especially important in the preparation of drugs. Molecular structure also affects the reaction rate. Water with a dipole structure reacts faster with sulfur dioxide, which also has a dipole structure, than with carbon dioxide, which has a flat structure. Enzymes. The catalysts that synthesize and break down biomolecules in living organisms are governed by the same principle as the acids and metals in organic reactions. The catalysts in living organisms, however, are usually protein molecules called enzymes. Enzymes are biochemical catalysts composed of amino acids held together in a very specific three-dimensional shape. An enzyme contains a region called its active site, which binds an organic reactant called a substrate. When bound, this unit is called the enzyme-substrate complex. Once bound, the organic substrate undergoes a very specific reaction at an enhanced rate. And in this illustration, you see the catalytic activity or the action of the enzyme lactase on its substrate lactose, the sugar meat, which consists of glucose and galactose. And when the substrate binds to the active side of the enzyme, which the enzyme substrate complex is formed, it causes the breaking of the bond between glucose and galactose. And so this is the starting material and the products of this reaction. And to break the bond, water molecule is added to the bond. It's an hydrolytic cleavage of bond by adding water. And the products will be galactose and glucose. And the enzyme, which is the catalyst, recovered unchanged in the reaction. The lactase enzyme catalyzes the hydrolytic cleavage of lactose, and the products are galactose and glucose. And my dear friends, this is the end of the topic. In here are some references that you can obtain and study. The next topic is carbon atom. And you can visit my website, biochemia.web, for more about organic chemistry, biochemistry, clinical biochemistry, and also the laboratory science. And you can also follow my Instagram account, biochemia.web. Don't forget to subscribe, click on thumbs up, and open notifications for further news. See you in our next topic. Goodbye.